Okay. Oh, there's some echo. I don't know. So, oops, I'm not supposed yet. Okay. We'll get started, and so let's see. Make sure my pen is working. Is that uh, not yet actually. Uh, yeah, it should be working now, but I have to. Oh, I forgot to. Uh, okay, so how I use the slide, but at the same time, I guess I will sketch something like with Suno, like whenever I need to sketch anything. So so basically, this is what we're going to talk about today. We will talk about camera models. It's more like um yeah, actually it's kind of weird because after so many classes we start talking about camera model, but we have a very rough model already, right? In the past, say the model that yeah, we'll see about that. This is a more detailed and complete camera model, and we'll also look into calibration a little bit. Calibration meaning that to yeah, and also you see like what do we mean by camera calibration? So it's like not that kind of camera calibration is if you're just a photographer that if you want to take some nice photo, most likely you don't need to do camera calibration. But for example, if you want to do 3D reconstruction with like structured by motion, that kind of like you take multiple photos and then you want to get the 3D points, like 3D locations of the environment of the objects, then you will need to calibrate your camera. So first of all, like what is a camera? Of course, everyone knows what's camera, but I guess most people don't know where these cameras, the name camera coming from. I guess actually, I may be a fun question. Like, anyone know that like, or like I should, I don't know. Maybe I just make it a partic. Yeah. Oh, maybe not. It's okay. I'll just. This is early. I guess maybe I'll ask that later on. Um. So camera actually, if you come of Google at Wikipedia, uh, in Italian it actually mean worm. Um, and it's actually precisely meaning that like when you're looking back like in ancient history, like both in Greece and in China, there's some like a very kind of like old camera is really a big room there. So you can see like the camera here, there's a okay, yeah, that's a camera. It's called like a camera oscura. It's actually a dark room like at UNC. So that's just have a pinhole there, and then you will have the light that kind of like uh, kind of go through the hole, and then like have the image like on this or this playing here, image playing here, and there's also like P camera stuff that like people uh like artists use like in the Renaissance. Like you see like why people suddenly draw so much better because they are cheating. Like at that time, like you see before that, like they know how to draw like in a perspective manner. Um, but then they actually created this device. Like at least some of the artists that created this device, probably Da Vinci developed that, like probably, and and you can see that like they when the light's going into that, like they have the exact image, right, kind of like reflected back on the screen there. So then when people draw, they can just draw like along whatever like they whatever the object like they. So and and we have the first photograph is actually long for a very long history, or like reasonably long, I don't know. It's like 1826, and you can still find the first copies in UT Austin. And it took a lot of time, like 8 hours to develop the photograph. Not develop, actually just expose, yeah, to put under the whatever the scene. Of course, in that case, you cannot have you need to have a pretty static object. Um, so and this is just a fun kind of like photos, like kind of showing that like um of course like when we do like computer vision and so on, oftentimes we're interested in the 3D uh 3D shape or like the 3D information of the target. But as you can see, like um, you can easily trick your brain and also your computer vision system, like the 3D and 2D info. I mean, with like a real 2D information to trick someone like have a different 3D perspective. So there's uh, there's another example. Like I don't know. Like okay, this may be a good to ask. Like uh, just like as a participation question, like what is this thing here? Can anyone see that? Yes. Uh, you can see clearly. I don't know if you can project this is the big screen, like this photo, not photo, this painting. And then like if you probably like see it at this corner, yeah, you can see that this is actually a skull. I'm actually a very well drawn skull. Um, and yeah, and okay, so now I guess getting a little bit like uh, the meat here. So we have this 3D information, and we try to like get I mean with the camera or like whatever like photo, yeah, camera. I guess usually in this case, uh, you project into like this 2D painting or like photo or whatever. Then maybe you want to from 2D like extract kind of like extract back the 3D information. So of course you need to understand this mechanism like from 3D world to the 2D image. So so we will start with the simplest model, right, the pinhole camera. So maybe it's better to sketch. Uh, so let me put the chat also. So if we have say yeah, the pinhole camera, basically you think of like even though like of course like uh if you remember like maybe you study optics in some of this physics class, then you probably have like this focal point here when you have like parallel lights that will just kind of like oops, yeah, I guess I can do a little better with this thing here. uh I can still not very straight. Yeah, okay, it's pretty straight now. So I have a straight. This is a light light beam coming through, and then I went with the lens is cut focus to this focal point here, and then we probably have a screen somewhere like maybe the sensor here. Then yeah, let's see. I probably have another light. Maybe how do I? Yeah. So anyway, So we have this will be like if we use a pinhole camera model instead, so probably we have the pinhole is here, then you have, oh, okay, maybe I shouldn't draw the pinhole camera even, but you think of like another way to think of that is that you have this is the image here, but we have instead like have image somewhere. A simplified model would be like I have an image somewhere, this is an image, but I have a projection plane here, and then we have this like the the center of projection. So I have like, you can imagine that like if you're seeing some photo, of course, like in reality, like you have the sensors like on your retina also, your this image that is projected, or actually maybe I should draw it like this. Yeah, that's what we learn in high school physics, I guess. The image, for example, the image here will be projected like kind of like invertedly on your retina, right? But let's use a simple model. Like think of like you have a kind of, this is a projection plane, and then like when you have an image, the image is simply like projected in front of you on this projection plane here. Okay, let me draw like this center projection is that here. So then you see the object is basically see her here, something like that. So therefore, like if your object, say for example, this is your object, maybe just a stick here. If you have a shorter stick, like but it's closer to you, then you look at the shape, the stick here. This will be the same height, right? So regardless, like even though like this is longer, but it's farther away, but it's like same height as this one. Um, and say like if I have the point location here, let's say like this is X, Y, and Z here. So and typically like people will use the coordinate Cartesian coordinate uh, system with the axis like pointing. This is the C direction, so I have like say this is C here, and then okay, let's say this is the origin here. Okay, I start with the origin is at the center of projections, and then this is a the center of projection. Just shorthand with COP here, and then let's say the point here is XYZ, right? So C, therefore like the C here is this length here basically. This is C here, and say the from the center of projection to this projection plane here, is D here. So okay, maybe a question, like a very simple, I don't know whether like it's a test of your what's that, trigonometry, I guess, or geometry. So what's the, so of course like with this one, let's say the height here is y, let's say, huh? This is y, and maybe like I in this case, let's say c is here, x. I can also have like x here. I'm drawing like there's no x here. I actually, I don't know what I should. If you see on this direction here, let's see. Let me see in this direction here. So what you see is that you have this projection plane, right? Projection plane, and I have my objects can be here like I have like x, y here, or maybe if I observe at here, maybe I call it x pi, y pi here. I see it on x pi, y pi here. And then like, but um, but yeah, but yeah, okay. Hopefully, my illustration is like uh, is understandable to you. Kind of can, so But here I'm drawing like the stick is like, okay, let me also like saying this stick like I'm drawing like kind of like shoot up like kind of vertically, like very kind of at 90 degree. So then maybe my x here, so there's no such x here. So maybe like the stick is something like that. So it's more or less like 0 y pi here, let's say, right? If I have the stick here, so I just vertically shoot up here. Um, so okay, let me ask a question here. What is y pi here? Given that like I have the tip of the stick here is at the point like x, y, c, or like maybe I write 0, y, and c here. And then like uh, at the screen here, you see like the location on the tip of the stick is actually at 0 and y pi at the projection plane. Oh, okay. Is the setup clear? You can yes. It is a simple trigonometry. Yeah. Okay. Yeah. Yes. I guess I asked some similar question in the past. Yes. Is that yes? Yes. Okay. Oh, okay. Fortunately, I guess at least I successfully asked the question to describe the question. But yeah, so that basically, as you can see, this triangle here, oops, maybe I used a different color here. So this triangle here is similar, okay, because this is right angle and this is also right angle. Eh? It's similar to this triangle here, the big triangle here. Okay. Yeah, so therefore, like I will have like this line over this line here, so that will be like y pi over d will be equal to say this line over this line here over y over z here. So therefore, like y pi will be simply y pi will be simply equal to d y over c, right? So okay, actually we have visited something like that before. Actually, it's not too surprising. And of course, the next x location will be the same as well. I have x pi should be equal to dx over z here. So we have the xyz location. Now, if I want to convert that to so this is like the camera mechanism, right? So you have the original 3D points in the three-dimensional world, XYZ coordinate. Now, after like some projection, some operation, hopefully we can make a matrix to x and y here, x pi and y pi here. Now, but you can see that I guess you see we have this problem before. Eh? If you just use the Cartesian coordinate, we cannot create a matrix to do this, right? Because I have actually x pi is equal to x over z, right? So it's not, yeah, you cannot basically create anything in the matrix form here. But we can solve this problem. So do you remember what we can, there's a name here from this Cartesian coordinate to what coordinate that we can solve this issue? Like anyone remember not anyone, this is another participation question. Like maybe you can just make up if you don't remember, like just, yeah. It's okay, you give a wrong. So my question is like, okay, this is Cartesian coordinate, right? Cartesian, how do I spell that? I'm trying to. it's definitely incorrect. Yeah, I'm sorry. Yeah, thank you so much. Yeah. So, and I can convert that into, anyone remember, H something coordinate? Then if I convert to that coordinate, then I can have like this multiplied by this matrix is into that. Okay, so a participation question for you guys. Yes. Oh, okay, it's close. It's not. Yes. Yeah. Homo. Uh. Uh. Yes. 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 Yeah. You can constitute this homogeneous coordinate. Uh. Then. Then it's basically you have x, y. It's basically just append with a one here. Eh? So now if I append with a one here, have x pi, y pi, and one, or it's okay because I remember the homogeneous coordinate here. When you append with a one here, what does it mean is that like you will have the in the homogeneous coordinate, the physical location of the actual point is invariant to scaling, because if I scale this like by s, let's say if I have like sx, 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 sy, sz, s here, this is equivalent because after all, if I have s here, I should kind of like normalize everywhere by s. So therefore, like these two, this coordinate values are actually representing the same point in space. So, okay, then if I have this guy here, let's see, if I multiply, I want to have something like that, right? I want to have like y pi or x pi should be equal to d multiplied by x over c. So what I can do is okay, oops, I think I flipped that. Is that, did I? Yeah, okay, not, I guess not. So if let's see, what should I do? Like x pi here. So if I multiply by, for x, probably I'll multiply by d here, and 0, 0, and 1. Let's see if it works. So if I do that, then what do I get? Actually, maybe I don't need that. Okay, maybe 0, d, 0, 0, and 0, 0, 0, 1, probably something like that. So let's see what we get. So if we have like this, then I have like dx, right? The first one I got dx here. The second one I got dy here. So then the third one I have, actually, no, actually I just want to put a 1 here, 0 probably. So the third one I got c here, right? So, but this is an equivalent of like dx over c, dy over c, and 1. And in this is like our x pi and y pi we want, right? So therefore, like this is basically our camera matrix. Of course, like, this is a camera matrix that we ignore in the simplest form because we ignore any intrinsic, I would say like in what's that word, like, or maybe the intrinsic like characteristic that the camera may have, that imperfectness, yeah, maybe that's a word, of the camera, or that we may kind of like include to, for example, like one thing is like maybe my camera have some skill thing that my sensor is not really completely very nicely, the sensor cell is very nicely oriented. So in the sense, we may include some parameter to describe those artifacts there. Another thing is like here we have assumed that like the camera center is precisely or like I should say, I should say that the origin is like precisely at the camera center, or like at the center of projection. So I may have like the world coordinate, and the camera coordinates are different. So I may have like the world coordinate system may not have the world coordinate system origins precisely at the center of projection. And also like I may have the axis of the world coordinate is not precisely aligned. For example, like I may not have the z-axis is precisely pointing like shooting like out of the camera center to the projection plane. So yes,
Professor Chang, can I have a question? Can I
yes,
ask a question?
yes,
So that center of projection,
yes.
is it equivalent to the pinhole in the dark room?
Yes, 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 yes. Wait. Yes, I think so. Like you can, yeah, yes, I think so. Yeah, if if the pinhole, if the pinhole model like is precisely the, yeah, you can consider that like that's precisely the center of projection. But if you're in the camera, then the center of projection most likely is that the center of the lens actually, if you can see here.
Uh-huh.
Yeah.
I see. I see. And this the plane is corresponds to like a film, right?
Yes, that's correspond to the, yeah, to the frame, or to the sensor, or like to your retina. Yes.
Uh-huh.
But
I
of course,
see.
physically, it should be like at the back, like instead of like. But usually, it's easier if you to imagine that it's on the front. Then
Mhm.
yeah,
I see. Okay. Yeah. Thank you.
yes, okay. Then now let's go back to some of the slides here. So this is precisely describing what we have earlier. So we have this virtual image, right? So if we, yeah, that's exactly what I, yeah, as you can see, the projection plane, you have the image plane like supposedly is at the back, like and you have the pinhole here. Is, yeah, as you said, like this exactly the center of the camera, or like the center of projection. And then you can think of the virtual, have a virtual image in front of that would be the projection plane, lie on the projection plane. um And so we have like something like this instead. So as we already discussed that, like, then the coordinate on the projection plane will be just x pi over d over x over d times x over z, and so forth. Then like we should convert to homogeneous coordinates. So therefore we will have this kind of like the simplest in the very nice setup. The simplest camera model will be camera matrix should be like this. So of course here, like earlier we have like DD1 instead, but it doesn't matter because know that if we are in the homogeneous coordinate, everything is invariant with respect to scaling. So if I scale the camera matrix by some s here, or like scale the coordinate by s here, it doesn't affect anything physically. So this is also yeah, perspective projection. So okay, and if you look at this kind of, this is a, yeah, this kind of like perspective projection. Um, um, you you can use that to model kind of things like pretty realistically, right? If you if you precisely try to draw things, like you should draw in a very 3D like uh, uh, painting or picture, then you should use the perspective projection. That simple equation we have earlier, you can draw something like very nicely like this. And sometimes you also like in games, like especially old school games, like you see that like people also use like orthographic, or like kids drawing, like maybe like orthographic projection. In the sense, you just think of the camera center is like in at the infinitely far away from the projection plane. So you can imagine it's like this is projecting to eventually like this line will be like kind of all of this line supposed to be kind of like intersect uh, at the projection, the camera projection. However, the camera projection is at minus infinity, so therefore, like these lines become parallel. And if we have that, then basically we have the projection matrix will be kind of like replaced by this instead, like simply. And you can see like you have the some example of like orthographic projection. You have something like that. This is like this kind of like some kind of old school like game, right? So I have this virtual 2D kind of stuff, and this is another example. So we can have like a little bit okay, by the way, we have this orthographic projection. We can kind of generalize a little bit. So you see like for this orthographic projection, like we have like this is like non-zero here. And remember in the perspective projection, we have a non-zero here and zero here, right? So if I generalize to have like the rest of like these two row here to be non-zero, then I will have like so-called like perspective projection. And by the way, this is actually like it's just a affine projection if you remember, right? So because we talk about warping, and also you did it in your homework assignment as well. Like if you have the most general case, we have the homography, then basically everything here is can be non-zero, right? Even though by ignoring the scaling factor, you may make the last one here, this is one. But if you have like a affine transform, then basically this will be the last row, like except the last element, like everything will be zero. And you remember, like if you have a affine transform, um, basically every line will be parallel after the transform, as here. Like if the original line lines in the original uh, original space is parallel, then like after the projection will also be parallel. So that's exactly what's happening with the purpose with the affine chart here. Like maybe I should call it purpose perspective projection as well. Right. So like in the 3D space, you have like this table here. I'm not sure I call this table or like I'm on chair or whatever. So these lines here are supposed to be parallel, right? After the projection is are also like still parallel. So okay, but for perspective projection, we won't have this if lines are not lines are parallel at the beginning. It isn't necessary to be parallel afterward, right? But they will be remaining straight. So if the line is straight at the beginning, they're still straight lines. And also like you can see like as I mentioned, like these lines here, apparently, if I look at the wheel here, the two lines here are supposed to be parallel, right? But they won't be parallel after the projection. And actually, they will converge to this vanishing point here. As you can see, there's a vanishing point. And if you learn to draw, like you can have a multiple vanishing points. So in this case here, you may have like 2 points, 3 points here. And for example, like I can have like 2 points here, 2 vanishing points, and 2-point vanish. I can't believe a painting like perspective drawing or perspective. Yeah, how do they call it? Like anyway, so perspective view with like 2 vanishing point here. So I can have like 3 vanishing point, for example. Like I can. Let's see if I can also show the. Yeah, that's I may want to. Oh, that's probably okay. So what I mean is like if I can have another vanishing point here, maybe like somewhere here. So then I will have something like this. Okay. For example, I set vanishing point here. So this is still like not, okay. It's not too good, but it's okay. So, and then I can make the, okay, anyway. So I'm not good at drawing anyway. So let's something like that. So so this gives you a perspective that like is like someone like the camera is here seeing in this um like more like you can think of the camera is more like near the ground, like something like, and kind of like shooting like in this view here. So if I have like the parallel, if I have the vanishing point is like at infinite, then it's more like you have the camera is like uh, it's more like kind of a horizontal view. So like you're seeing like just directly kind of like horizontally. But this one, instead you have the vanishing point is here, like you, it's more like you're seeing like kind of a little bit tilted like uh, vertically, like trying to like seeing upward a little bit with an angle. So anyway, so yeah, just uh, a little bit about drawing. So okay, yeah, this is just repeating what we said like about like what will be like preserved like or like invariant after perspective projection. So okay, now get to a little bit more complicated. I shouldn't say complicated, but as we mentioned earlier, we ignore some of this assumption. We have this simple assumption that the first of all, like we ignore the internal parameters of the camera, and secondly, like we assume the coordinates of the world and the coordinates of the camera are completely aligned. So now let's just maybe it's even though like the yes, yeah, maybe it's still, even though this it's easier to sketch here, I guess. So so now we assume that the camera coordinates can be different from the world coordinate here. So, and I have the camera coordinate, have the UVW. So I have the W is pointing, actually pointing this direction. Maybe if I, yeah, it's okay. UVW, yeah, okay. I have W pointing in this direction here. I don't know why you want to point this direction, but it was okay. Let's say the W is here. So what we want to is that UVW is supposed to align with XYZ here, right? So what should we do? So we want to, first of all, like what we can do is like we have like some point in the world coordinate. I need to make sure that I should convert the points from the world coordinate to the camera coordinate, right? I have the camera coordinate is this UVW here. So then if I have a point somewhere like here, if you remember earlier, in the UVW coordinate, let's say here is also D here. So if I have some point here, let's say U pi, or okay, maybe I call U tilde, V tilde, and W tilde here, let's say, then it should eventually project it to like U times U over W tilde, U tilde over W tilde times D, right? And then like V tilde over W tilde times D, something like this, right? But I need to first like convert this original, let's say the coordinates X, Y, and Z. I'll convert to like this UVW first before I can move on. So is that clear? So now, so what should I do? So let's say my original coordinate is x, y, and z, right? First thing first, maybe I should move the center, the origin of the world to be aligned with the origin of the camera. So let's say if I have a let's say if there's a translation of C here. Let's say this is C here, or maybe the other one. Let's say if I think of like according to the world coordinate, let's say the camera, the center of the camera, let's say is a location C here. So then what I can do is I can simply have X, Y, Z, or like maybe I just put it as a vector form here. Maybe I call just a X bar here. I can have, if I want to convert this coordinate, I can just have X bar minus C, right? Either minus C or plus C. So let's see. Yeah, as I'm showing here, right? So I have the original camera here. So let's say if I need to move, let's say the camera location here is C according to the world coordinate. So if I want to move this camera center to here, then I can just say or the other way around is if you can think of like any coordinate here, if you want to move to this camera coordinate system, then I should just have like this point minus C, right? So, or like you can think of really the camera center now move to here, translate the camera center to the origin of the world. So this translation is pretty simple, right? So we have, and we kind of like studied this before. So if we have a translation, yeah, I should really ask you earlier, but it's okay. So if we have a translation with this, the translation is by C here minus C here. So then the translation will be just, I have this coordinates, let's say X, Y, C, 1, just simply multiply by this translation matrix T here, right? So yeah, because if I do that, so maybe okay, maybe I elaborate anyway. If I do that, what do I get? So this T here, this T here is 1, 0, sorry, 1, 1, 1, 1 minus CX, let's say minus CY minus CC, right? Let's say my C here is like CX, CY, CC here, right? X, Y, C1. So then I multiply that, I will have X minus CX, right? And then Y minus CY, and C minus CC, and then 1. Yeah, so in this is a simple translation, right? So now I need to rotate that also. So to rotate that, I will use a rotation matrix like this. So it's UVW1. So indeed, like this rotation matrix should get you what you want here. We can verify that. So note that like after the rotation, what should we get? We should have let's say, okay, what should we have? Like let's say if I have the camera coordinate is like this, right? Originally, I have W is here, and V here, U is here. So what I want is like I should have if if I have a vector is pointing, let's say the U direction here, then the vector after the rotation here, I should have a coordinate like should I ask you guys or not? Actually, let's see. Let's think about that. Yeah, it's okay. Okay. So yeah, maybe I should still ask you later, but then you can pause to think a little bit. So what I want to say is like after So let's pause a little bit, make sure everyone is at the same page. So let's say if I have some, the objective here is like some point in space. Okay, let's go back to here maybe. So if I have a vector here, let's say maybe I just put a vector here, a unit length vector here, that the length is 1 here, pointing at u direction here. Now I have this translation that move this camera center to the world origin. So I have this translation is like I minus c 1 here, right? And my rotation, let's say is going to align my cameras. So I have this vector here. Let's say I have this vector here, call it, give it some name here. Maybe I just call it A here anyway. So A vector here. The A vector here is like starting at the camera center, shooting in this direction in this U here with unit length here. So after this translation of this camera center, and after this rotation here, the rotation supposedly to align the world coordinate with the camera coordinate. So what do you expect this output here should be? So maybe I should use a homogeneous coordinate system here. So therefore this A1 means a A1 here. So so what do you expect like this supposed to be like? I have some point in space here, or you can think of a vector in space here, starting at the camera center and go along the direction of u here. I'm a unit length vector, and then then after this transform here to align this camera to the world coordinate to the yeah, actually you can even ignore this one here. Think of like the goal here, the objective here. My objective here is like trying to align this world coordinate with the camera coordinate, right? So then after this alignment here, if this is this operation is like correspond to this alignment, moving the center to this, align these two center of origin together, and also like rotate the world coordinate to the camera coordinate. That's a good try anyway. So that's also this here also. There's a rotation here. Yeah, but I guess that this is a good place to pause, like because I guess is oh yes, you can ignore the entire thing. Therefore, like if you just look at this together, you can ignore the entire thing, right? So if you just look at this one here, then you have this C coming up, right? So anyone give some thoughts again? Let me repeat. So make sure everyone at the same page. So Now we simply have a vector, right? So I guess this is a kind of key, right? We have a vector starting from the world coordinate, the camera coordinate, camera center. I'm just a unit length vector, like length u here, uh, with sorry, not length u here, length 1 here, like pointing at the u direction here. Now I have some operation to align this camera center. So this operation will first I do translation and then do rotation, right? First translation and then rotation. But you can think of like basically this combined operation simply align these coordinates, right? So trying to move, you can think of like it's like moving this world coordinate system to align with the camera coordinate system. So originally, this vector is represented like in the world coordinate system. So then if I have like everything aligned here, oh yeah, actually I should emphasize this also, right? Originally, you can, this line, this coordinate here is the vector in space here, of course, is here, but originally this vector is like according to this world coordinate system here. Making more and more like sketchier. In the world coordinate system here. Now, after the projection here, is in the camera coordinate system. So no. Any other kind of. So yeah, okay. I guess I don't have a really very well posed question here. If I put in these numbers, it may be more obvious, but it's pretty hard to put in some numbers here. So okay, let me just give an answer here. So what I mean is yeah, actually maybe I can put in some numbers. Maybe I have in the original world coordinate, yeah, I put some number 1, 2, 3 here or whatever it is. It shouldn't be 1, 2, 3 because it has to be maybe like square 1 over square 2 or 1 over square of 2 of 0, something like that. Or I should have some shift here. Maybe, oh yeah, actually it's okay. Like maybe, actually I can put anything actually. Maybe 3, 4, 5, let's say. What I mean is like, basically like for whatever this one here, because it's actually representing in the camera coordinates, it's like from the center shooting from U here, right? I'm shooting in the direction of U here with a unit vector. What we want to project it back should be something like 1, 0, 0, 1 here. So, and if I already did the translation here, then I should have like this vector, of course, should be like unit norm here as like this one. So what we are saying, like, actually, I just want to say that if we already did the translation here, maybe I will draw it somewhere here. If I already did the translation here, the rotation, as I mentioned, should be just like U transpose, V transpose, and W transpose 1 here. Because like, if you think of like, you have the vector here is actually U here. For example, if I have U here and 1 here, then precisely I will get like 1, 0, 0, 1 here if I have U here. What I mean by U here can be like UX, UY, UC here. And my U here is basically UX, UY, UC here. And because a UVW kind of like normalized and orthogonal, so I have U multiplied by U here. This will just give me like 1 here and Okay, let me explicit write it like ux, uy, uw. So this is vx. Similarly, vx, vy, vw. Sorry, not vw. uc, vc, and w x, wy, wc here. So right here, I should write u here. So if I have normalized, I should have like ux squared plus uy squared plus uc squared equal to 1 here. So therefore, when I multiply this guy, you see like this is exactly equal to ux squared plus uy squared plus uc squared. So, and that give you 1 here. And then second one, I have like this dot product with this guy, right? And the dot product between these two guys, because u and v are orthogonal, so I get 0 here. And w and u dot product with one another, I get 0 here as well. So I get something like 0, 0, 0, 0, 1, and this is 1, so I have 1, 0, 0, 1. So okay, I guess I just want to I just want to like reason that like why this rotation matrix is equal to this guy basically. So anyway, so therefore like if you see like if I have the camera center and the world coordinates not aligned with at the beginning, what's ax, ay, ac, one is
Professor Chen,
yes.
so if the original vector was A, so AX, AY, AZ is the each component of this vector
Oh
A?
yeah. Okay. He is actually is a vector here. Oh yeah, yes, ax, ay is, but that's here. It yeah you here is like before translation. So after, so basically my ax, ay, ac one is equal to ux plus c. Let's see, yeah, something like that. Uy plus c and uc plus c one, something like that. I say I want to make sure where's the c, but okay, either plus c or minus c. So yeah, that's one. So after
Yeah.
the translation will be simply ux, uy, uc. Yeah. Yes. So you have like ax, something like that, multiplied by translation, you get like ux, uy, uc basically, and then like yeah, with the rotation here, you will just get back like just 1, 0, 0, 1. Yeah. So
I see.
yes. So therefore, like the translation and rotation matrix is like quite well defined. As you can see, it's just like I have the translation like this way earlier, I have the rotation like this. So if we need to kind of take, as I mentioned, like if we assume the world coordinate and camera coordinate does not align to begin with, then we have this new matrix coming up first before we have this projection. Earlier, the perspective projection. Earlier, we have like 1 over d or like dd1, right? But here, let's say like we can absorb this d here into the intrinsic matrix later on. So then now we have a more complicated like camera matrix or like more complete camera matrix that have the projection here, have the rotation, translation. This whole part here, we call it like the intrinsic, extrinsic camera matrix, or the extrinsic component, because like the intrinsic component really is related to how the sensor are oriented in the camera and so on. And that's something that like you cannot change it like once the camera is produced or manufactured. But the intrinsic component, of course, like where you put the camera and how do you define the camera center can all be changes. Like it's not depend on the intrinsic property of the camera itself. So now we can get to the intrinsic parameter here. So some of the intrinsic, also, but that's just repeating what we mentioned. So this is the original point in the world coordinate. So I should first do the translation rotation. And Oh, and by the way, like my translation matrix is like this, right? And the rotation matrix is like this. When I multiply this, I'm also with the projection matrix, I multiply them together. So of course, like this, multiplied by this, I can do a kind of block matrix multiplication, right? So this should give me, if just I have this multiplied by this guy here, I should have R times I plus 0 times 0, right? So I should have R here, and then R times T, 0 times 1. So I have like RT here, and I have like 0I, 0, 0. So I have 0 here, and 0T, 1, oh wait a sec, yeah, COT and 1 here, I have 1 here, something like that. So I multiply this, we get this. Now if I multiply the projection matrix here, this is basically nothing, just like taking the first 3 rows and ignore the last row, right? So therefore, like the multiplication of this whole thing, I will get RT here. So therefore, like this, the whole thing is like R and RT. And I can just take this part. Sometimes I can call this a small t here as well. And yeah, and then we have the intrinsic common matrix is K here. So now we can go deeper into this K here. So K, first we can like first let's like ignore the extrinsic common matrix completely. So we can ignore this part here if we assume the common center are aligned, right? So then in the sense that this rotation and translation will be 0 and rotation will be just like identity. So will be just like equal to identity matrix times 0. And I can have the K matrix here. So okay, this would be like just the extrinsic matrix would be just I0 here. And for the intrinsic matrix, let's assume that like we have like almost the simplest case. So we'll just have like that's some the aspect ratio will be the same like for both horizontal and vertical direction. So then the scaling along these two axes is the same. So I can have the same scaling factor like di here, or like just d here. And the optical center, let's say, is just right here. So then I will have like the intrinsic common matrix will be like this. So let's say like if I have the camera center, it's like shift, not the camera center, as the center, the sensor of the center of the sensor is shifted, or that you call it the optical center is shifted by U and V here. Then again, I can shift it back by another translation here by, if you, it will be just like multiplying by another translation matrix, like something like U0, E0, and 1, something like that, right? So then I will have like the intrinsic common matrix have like additional U0 and V0 here. Yeah, I know it's a little bit silly because why don't you want to define your kind of like optical sensor center like as here instead of somewhere else? But anyway, like if it's not right at the center already, then we can shift that like with this modification of the intrinsic matrix anyway. So and then like if we have like some kind of like variation of aspect ratio also like vertical horizontally, maybe like I have the sensor, it's not exactly square. Maybe the sensor cell is like rectangular. So maybe like in one direction is bigger than the other direction. So then we probably will need to kind of like take care of this like this scaling factor like into the intrinsic matrix here. So therefore like we can put in an alpha, something like that. And finally, maybe if my sensor even kind of like not very well manufactured, maybe like it's like slightly, or like simply like you can think of like if you have like the sensor cell here, for example, for the camera, it's not exactly aligned, like maybe a little bit like rotated. Actually rotated, then you should rotate back. Maybe it's like you really have the sensor cell is like not aligned so well. Then you have some skewing here. So then you can take care of the skewing with the skewing factor here, as here. So therefore, like this is our kind of like the complete uh, intrinsic camera matrix can be modeled by something like this. So so this will be our overall camera matrix then. Like so we have the to summarize, we have like the extrinsic like RMT here to take care of like the fact that my camera centers are not aligned. And then I have the intrinsic like K here to take care of any imperfectness that is like introduced during manufacturing of yeah during the production of the camera. So yeah, and any question here, is that clear? So this is basically the entire camera matrix that if I put in some coordinates in the world coordinate, some coordinate values in the world coordinate, after this camera matrix projection, this matrix multiplication here, I should get back the coordinate, the corresponding coordinate on the projection plane. So
What is W?
W is like just some arbitrary scaling here. Because remember that if I am in the homogeneous coordinate system, scaling doesn't matter. So if I multiply this entire thing here, this doesn't this value here doesn't necessary to be 0, or sorry, to be 1. So it can be W. So I can pull this, just put the scaling factor out. So,
I see.
yes.
Just overall scaling factor to make a UV1, right?
Yes, yes.
I see.
And this this scaling factor has no physical meaning here. Yes.
Yeah. Okay.
Yes. So camera matrix. Okay. I'm not sure. I should. Okay. Maybe I can. Let me find if I still have it here. Yeah. This is just something I. Oh no. This is like something else. Let me remove this one. Oh. Okay. Yeah. Okay. So yeah, I can't forget like the detail of this code, but anyway, maybe I will want it anyway. So it's something I created like a couple years ago, just for fun. So this is I have some 3D points. I got some point coordinates from the I downloaded somewhere. I guess I forgot where I downloaded from. So this more or less you can see like this is some trees here. This is a house, or maybe like this is a light pole here, and or electricity pole here, and here I'm showing like the translation of the world coordinate. Yeah, I have a bad feeling about this like of the fan here. Okay, so so hopefully you guys can hear me. So, hi. So you guys can hear me still? Hello?
Yes, we can hear you.
Oh, okay. Yeah. Apparently, like my my uh my laptop hangs. So I'll use this backup laptop here. Let's say. Um. Hopefully, we won. Uh. Wait a sec, I guess. Oh. Uh. Oh. Okay. Oh, yeah, sorry, I didn't share this screen yet. I forgot. Give me a sec. Yeah, but for this one, I cannot see your chat here. It's, because this does not connect to another monitor. But yeah, we are almost time. So I guess uh, um, okay, what I'm going to do, maybe I continue to talk about the slides, then maybe I come back later on next time to show some demo. But let me just get back to the slide. So I need to find my slide here. Okay. So maybe just some final things to mention. So note that like for the camera models that we have earlier, we ignore some of this radial distortion. For example, if we have the lens here, because of the lens is not exactly, we have a pinhole cameras, right? So if I have the lens, there would be some different kind of radial distortion. So you have this barrel distortion, for example, as you can see here, or like this pin cushion like distortion. And yeah, you see that like we can remove the distortion a little bit, like have some kind of correction here. So if we have like, so let's say that just have this out here, it's like from the center of the camera, or like if you think of like out, it's like basically like at the projection plane here, after you do the projection here, let's say you take the center of the screen here as the origin, and the R is basically just like how far from the center here. And then because typically you have the barrel, you consider the barrel distortion is just, and also the plane cushion distortion is just like symmetrically kind of distorted like from the center. We can model this distortion like with this quadratic function with respect to R here. Then we just need to find these parameters like K1, K2, and so on. We won't talk about how to find that. Like, but for example, in OpenCV, if you do some kind of calibration, you're able to like fit this. Maybe just a quick few. Oh, okay, I don't know. I'm time, but let me just really quick few words here. Okay. Anyway, I guess I should really stop here. So sorry about the technical difficulty. Again, I don't know why my computer keep hanging like recently. So, but do you guys have any questions? If not, then I will continue next. I mean, not next, but this Thursday. All right, I need to see your chat, but I cannot find your chat anyway. Yeah, I guess I can just stop sharing. So by the way, put up the new homework is related to like what we talk about. Oh, okay, it's not as much related to the, but it helps if you understand everything today. But it's more related to next class, I guess. I will when we talk about epipolar geometry. So yeah, you can take a look of the homework, but don't worry too much about that if you don't understand what's going on. So we will talk more about that next time. So, okay, hearing no questions, I will see you guys this Thursday then. Bye now.